a sound source moves towards a stationary observer with speed 1/4 of speed of sound in air. The ratio apparent frequency heard by observer divided by frequency emitted by source. I will consider this one is the source and this one is the observer. Source is emitting the sound wave. I will consider wave of sound is V. Frequency F0. Now the sound source moves towards a stationary observer. Then speed of source should be towards the observer and speed is given as 1/4 of speed of sound in air. Then we can write equation for the Doppler frequency, apparent frequency. F dash equals velocity of wave relative to receiver divided by velocity of wave relative to source multiplied by actual frequency. Then F dash equals velocity of wave relative to receiver. You have to consider that receiver is at rest, but actually receiver is at rest. I will consider receiver. Therefore, receiver can see the actual velocity of source and actual velocity of wave. Now we have to get the velocity of wave relative to receiver, then wave relative to receiver, velocity is V. And this one is velocity of wave relative to source. When getting velocity of wave relative to source, we have to consider that source is at rest. Therefore, we have to give an opposite velocity for the source, and we have to do same thing for the wave. Then this velocity and given velocity, it should be V over 4. These two velocities are in opposite direction. Therefore, we have to subtract V minus V over 4. V minus V over 4 times F0. Now we have to find ratio between apparent frequency and real frequency. V divided by V minus V over 4 is 3 over 4 of V. 3 over 4 V. Then we can cancel out V and V. Answer should be 4 over 3. Then answer is 4. So it's a source, it should be a source. A source is moves towards and away from a stationary observer. O, as shown in the figure, the ratio of velocity of sound in air V0 and velocity of source Vs. By considering V0 over V is 11, the ratio of the maximum and minimum apparent frequency heard by observer will be. We can use equation for the apparent frequency. F dash. We can see a maximum apparent frequency when the source is moving towards the receiver. It is like this. We can get F dash maximum velocity of wave relative to receiver. Receiver is at rest. Therefore, we can see velocity of wave without any change. V0 divide by when getting velocity of wave relative to source. Source is moving towards the receiver like this. Therefore, we have to subtract velocity of source from the velocity of wave. V0 minus Vs multiplied by actual frequency. Then we can get minimum apparent frequency. When getting minimum apparent frequency, I will draw the diagram. source should be moved away from the receiver. Now, numerator is velocity of wave relative to receiver. Receiver is at rest. Therefore, he can observe V0 velocity. There is no change in velocity of wave relative to receiver. When getting velocity of wave relative to source, we have to give an opposite velocity for the source, and we are always considering wave towards the receiver, velocity of wave V0. Then we have to give same velocity for the V0 velocity, Vs. V0 plus Vs multiplied by actual frequency. Now we have to find the ratio between these two frequencies. Then we can cancel out F0, V0, and we can get V0 plus Vs divided by V0 minus Vs. They have given V0 over Vs is 11. Then V0 is 11 times Vs. Then we can substitute V0 is 11 Vs plus Vs divided by, again V0 11 Vs minus Vs. 12 Vs divided by 10 Vs. We can cancel out Vs and we can cancel out remaining parts by 2. Divide by 2, 5. Divide by 2, 6. Then answer is 6 over 5. Fourth one is the correct answer. The sound source emitting signals at a constant frequency F2 moves along an arc of a circle with constant speed v as shown in the figure. The stationary observer is located at point X. Point O is the center of circle. As the source moves from A to B, the variation of frequency F heard by the observer is best represented by. We know that when the receiver and source when the distance between receiver and source is decreasing, we can observe a higher frequency than actual frequency. Therefore, when the source is moving from this point to this point, frequency is a higher value than the actual frequency. Apparent frequency is a higher value than actual frequency. At this place, we can observe actual frequency because of this moving direction is perpendicular to the line joining observer and source. Therefore, frequency should be a greater value and it should be changed like this. This one is the real frequency. We can observe real frequency when the source is at this phase. And after passing this phase, the distance between receiver and source is increasing. Therefore, we can observe a frequency less than actual frequency. When getting the answer, we have to consider that receiver is not at the center. If receiver is at center, there is no change of apparent frequency because of there is no change of distance between receiver and source. Then answer is 5. A train travels along a straight track. Another train the same direction behind the first train at the same speed. we have to consider same speed. The train blows the whistle of frequency f0. The apparent frequency of the whistle heard by the stationary passenger sitting in the second train f. Then you have to get relationship between s and f0. Both trains are moving with the same velocity in same direction. It means there is no relative motion between two trains. Therefore, he can observe a frequency equal to the actual frequency. Then f should be equal to f0. Answer is 3. An observer is moving at a speed 40 meters per second towards a stationary siren sounding at frequency 600 Hz. If the speed of sound in air is 320 meters per second, what is the frequency of sound heard by? Now I will consider corresponding receiver and source. Siren is at rest. Therefore, source is at rest. Receiver is moving towards the source with 40 meters per second speed. This sound source is emitting sound in all directions in spherical path. But we have to consider the sound component in the direction of receiver. Now velocity of sound is 320 meters per second and frequency is given as 600 Hz. Again I will write the equation related to the Doppler frequency. F dash equals to velocity of wave relative to receiver divided by velocity of wave relative to source multiplied by real frequency. We have to find the apparent frequency f dash. When getting velocity of wave relative to receiver, we have to consider that receiver is at rest. Therefore, we have to give a velocity in opposite direction and we have to do same thing for the wave. Then we can get 320 plus 40 is the relative velocity, 360. Then we have to get velocity of wave relative to source. Source is at rest, therefore there is no change of velocity. We can observe real frequency. It means velocity of wave relative to source is 320. We have to multiply by the actual frequency 600. Then we can cancel out 32 divided by 48 divided by 490 divided by 42 divided by 415 divided by 2 1 divided by 2 45. Then we have to multiply 15 into 5 75, 7 remaining, 15 into 4 60 plus 7 67, 675 Hz. Then answer is 2. A train moving along a straight track at a velocity 30 meters per second emits a sound of frequency 600 Hz. If the speed of sound is 330 meters per second, the wavelength of the sound propagated forward along the track will be. We have to consider the source. Train is moving with a 30 meters per second velocity. We have to consider receiver is behind the train. It means we have to consider a receiver at rest this pace. Then I will consider velocity of wave 330 and frequency 600 Hz. Then we can use apparent frequencies, velocity of wave relative to receiver divided by velocity of wave relative to source multiplied by real frequency. But we have to find apparent wavelength. We know that V equals F lambda. Then lambda is, F is V over lambda. We can use V over apparent wavelength lambda equals to velocity of wave relative to receiver. Receiver is at rest, therefore he can observe real velocity of wave divided by velocity of wave relative to source. We have to get that source is at rest. It means we have to give opposite velocity for the source, and we have to do same thing for the wave. Then 330 and 30 in opposite direction. We have to subtract 300 multiplied by real frequency 600. We can substitute velocity of wave is 300. No, 330. Then we can find the lambda value. We can cancel out 330 and 330. 300 divided by 301 to lambda dash is 0.5 meters. It means 50 centimeters. Then answer is 4. A driver sitting in a parked car seen another car moving directly towards his car, sounds his horn. The frequency of the horn of the parked car is 340 and the speed of sound in air 340. If the driver of the moving car detects the frequency of sound at 348, the speed of car is. Now, source is at rest. Receiver is at moving car towards the parked car. Velocity of, we have to find the velocity of this one. I will consider it as V, velocity of receiver. Then we can consider wave, frequency of wave 340 Hz and velocity of wave also 340. Then we can write apparent frequency, velocity of wave relative to receiver. Relative to receiver, we have to give V velocity in opposite direction and we have to do same thing for the wave. Now, when considering velocities in wave, there are two velocities in same direction. We have to get sum of velocity, 340 plus V. And velocity of wave relative to source. Source is at rest. Therefore, there is no change of velocity, 340, multiplied by real frequency 340 Hz. Then we can substitute apparent frequency. It is given 348. We can cancel out 340 and 340. Then 340 plus V. We can find the V value 8 meters per second. Velocity of this car is 8 meters per second. Then answer is 5. The car travels at a speed of 20 meters per second towards a stationary sound source that produces sound at a frequency of 1 kilohertz. Waves that are reflected from the car and return to the source are used to produce the beats with original wave. The approximate value of the beat frequencies. Use the speed of sound in air is 320. Now I will consider initial situation. It means car is traveling with 20 meters per second velocity towards a stationary sound wave, stationary sound source. Then I will consider receiver is at the top. Then we can consider wave frequency is 1000 Hertz. 1 kilohertz means 1000 Hertz. And speed of wave is 320. Apparent frequency for this receiver, it means receiver at car, F1 equals to velocity of wave relative to receiver. In getting velocity of wave relative to receiver, we have to consider that receiver is at rest. Therefore, we have to give a velocity opposite to the initial velocity, 20. And we have to do same thing for the wave. Now there are two velocities for the wave in same direction. Therefore, we have to add 320 plus 20, 340. Divide by velocity of wave relative to source. When getting velocity of wave relative to source, source is at rest. Therefore, there is no change of velocity of wave. 320 multiplied by real frequency 1000. Then we can consider the second situation. For the second situation, source is this one. We have to consider reflected wave. Then wave is moving towards this direction and receiver is at rest. Then we can get frequency observed by this receiver, F2, equals to velocity of wave relative to source, velocity of wave relative to receiver. Now receiver is at rest, therefore he can observe 320 real velocity of wave. And velocity of wave relative to source, we have to give opposite velocity for the source, 20. Now wave is moving in this direction. We have to give same velocity for the wave. Velocity of wave is in opposite direction. We have to subtract. Then 320 minus 20, it means 300 into F1. Now we can substitute this F1 value to the F2 equation. F2 equals 320 divided by 300 into F1 value. F1 value is this one, 340 divided by 320 into 1000. And we can get an approximate value. It is 1133.3 Hertz. Now, there are two frequencies heard by receiver at this place, emitted one and reflected one. Emitted frequency 1000 Hertz, reflected frequency 1133 Hertz. Therefore, beat frequency is the difference between two frequencies, F2 minus F0. F2 value is 1133.3, F0 value is 1000. It is the emitted frequency. Then we can subtract 133.3 Hertz. Then approximate value is 133. Answer is 5. Waveform emitted from the sound, from three sources of sound. The figure separately represents sound. We have to consider movement of three sources. In the first diagram, we can observe that it is like this. Wave progressions are near by near. In this direction, it means the difference, the distance between two wave progression is a small value. At this direction, therefore, this source should be moved in this direction. In opposite case, we can consider this object should be moved, this source should be moved in right hand direction. And for the third one, we can see a wave pattern like this. It means he can't observe, a receiver in this direction can't observe wave because of the source is moving with velocity of wave in the corresponding medium. Then moving left hand side, moving right hand side, then moving right hand side with the velocity of sound. Then answer should be 5. The source of sound is moving with velocity Vs, emits a sound wave of frequency F0, and observer O moving with velocity V0 as shown in the figure determine the frequency of sound as F. Which of the following statements are true? We can get that when the distance between, gap between receiver and source is increasing, receiver can observe a wave frequency less than apparent frequency. When the gap is increasing, apparent frequency is less than real frequency. When the gap is decreasing, apparent frequency is greater than real frequency. Then we can get fourth one is the correct answer. Vs minus 60, it means Vs minus 60. In fourth one, Vs minus 60, Vo minus 20. Gap is decreasing, therefore apparent frequency should be greater than real frequency. Then answer should be 4.